Okay, so chapter 28 is about quantum physics. So I've picked out a few examples of problems to work out of there. So we'll start with that. So we're going to start with chapter 28, number 13. All right. It says that zinc has a work function of 4.3 EVs. So this is zinc, and its work function is 4.3 electron volts. Okay. It wants to know what is the longest wavelength of light that will release an electron from a zinc surface. Okay. So we're going to need to, first thing is to convert the work function to joules. All right. And so what that means is we need to take 4.3 because we can't do anything with EVs. And we have to remember that one EV from back in chapter or unit 2 is 1.6 times 10 to the minus 19 joules. So that's the first thing we need to do is convert that. Okay. Then it says, what is the longest wavelength of light that will release an electron from the zinc surface? So we want to find the wavelength that's the longest, and that's going to correspond to the frequency that's the lowest, because the longer the wavelength, the lower the frequency, and we learned that in the chapter about light. So what that means is we're looking for the cutoff, or sometimes what's called the threshold frequency, because remember, that's the lowest frequency of light that will release photoelectrons from a metallic surface in the photoelectric effect. Okay, so the equation for the photoelectric effect says that the energy of the photons is equal to, so the energy of the photons is HF, is equal to the work function of the metal, which we know, plus anything that's left over will go into the kinetic energy. Okay, now this is the idea behind the work function, and we talked about this in the notes. Okay, the photoelectric effect said you get one electron for one photon. So if the photon has more energy than what you need to eject the electron, it doesn't get you another electron. All right, the energy can't split up. It's got to all go to that one electron. So that's where we get this K max. But in the case of this problem, it says what's the lowest frequency. So for this problem, we're assuming that K max is 0. There's no leftover energy. We've got just enough to release the photon from the surface. So the lowest frequency is going to be HF, and this is going to be cutoff or threshold frequency, is equal to the work function. So the frequency of the lowest frequency photon that will work for me is the work function in joules. Now you got to get it in joules, which we already did that, divided by H, where H is Planck's constant, and you look that up in your book. And that's 6.63 times 10 to the negative 34 joule seconds. Okay, so I know what that is. I know what this is. So that gets me the frequency. I want to find the wavelength. So I have to go back and remember from chapter 1 how to do the wave speed equation. So the speed of light is equal to the frequency times the wavelength of my light. So the wavelength of my light is just going to be the speed of light in vacuum divided by the frequency. And in this case, it's going to be the cutoff frequency. I know this is 3 times 10 to the 8th meters per second for vacuum. So I know everything I need to know to find the longest wavelength. Okay, so when it says the longest wavelength, that gives you the lowest frequency, because they're inversely related. The bigger the number for wavelength, the smaller the number for frequency. And then that's the cutoff frequency for the photoelectric effect. Okay, so that's part A. All right. Part B says a 4.7 EV photon strikes the surface and an electron is emitted. What is the maximum possible speed of the electron? Okay, so in this case, we've got the energy of the photon, HF, is equal to 4.7 EVs. Now, they've already solved for H times F for me. I don't have to do that because they told me that this was the energy of the photon. So the first thing I need to do, again, is convert this to joules. I can't use EVs in this equation. So I need to convert this to joules. So 1.6 times 10 to the minus 19 joules. And that gives me the energy in joules. So then I'm going to use my work function, or I'm going to use my photoelectric effect equation that says H times F is equal to the work function plus the leftover is the kinetic energy. Okay. So I know H times F from right here. They told me the work function in part A. So I got that from part A. All right. And so the K max is equal to HF minus the work function. So I just take those two numbers, the one I just solved for and the one I found in part A by converting to joules, take the difference between them. They're wanting to know the speed. All right. So kinetic, then I go back to the definition of kinetic energy. That's just 1/2 mv max squared is equal to whatever this difference is that I'm going to find those two numbers. I know it's an electron, so I look up the mass of electron, which is 9.11 times 10 to the negative 31 kilograms. I know what that is. Okay. So the only thing I don't know in there is V max. That's going to give me, I'm just going to solve for V max. Now, what you're going to find about these problems in this chapter is the math is actually fairly straightforward. It's not solving simultaneous equations. It's not, trying to do the quadratic equation or any of that stuff usually. It's just adding and subtracting and taking a square root every now and then. But you've got to know what all the terms mean to be able to put stuff in the right place. So just make sure you familiarize yourself with the vocabulary here. That's going to be more important. Okay. All right. So that's all of chapter number 13. Okay. All right. Let's go on and do, let's see. Let's do 21. All right. 21 says, what is the wavelength in nanometers of a photon with energy 0.3 EVs, 3 EVs, and 30 EVs? For each, is this wavelength visible, ultraviolet, or infrared light? All right, so I'm going to start with 0.3 EVs. Okay, 0.3 EVs. So I need to find the wavelength. So this is the energy. So the energy is H times F. Okay, but if I want to find the wavelength, what I can do is I can remember that F is C over lambda. That comes from the wave speed equation that we just saw in the previous problem. So I can rewrite E as HC over lambda. Now, I don't like any of these in EVs. I need to convert to joules. So I'm going to convert 0.3 EVs to joules. Okay, so I'm going to convert that to joules. Then, so lambda, if I solve for this, is going to be HC over E. And I know all this stuff. I know H is Planck's constant. I know this is the speed of light, which I know, look up. And I know E is this thing right here, whatever that is converted to joules. So I know all that stuff. So I'm going to solve for lambda. And then I'm going to go back to my chapter on light, and I'm going to look up where that number falls. And I'm going to figure out if it falls in the infrared or the visible or ultraviolet. So I'm going to look it up in the light chart to find out if it's IR, visible, or UV. So once I have lambda, I can go to that chart and figure it out. Okay, and that's in that chapter that we just got through having the test on light. Okay, you're going to do that same thing for all three of those values of energy. So 0.3, 3, and 30. Okay, so same process for all three parts. So I'm not going to go through B and C again, because it's going to just be the same thing, and you're just going to have a different value up here where you convert to joules. Okay. All right, so that one's not too bad. Just again, got to make sure you got to convert to joules. All right, let's do one more. Let's do problem 34. Problem 34 says, what is the speed of an electron? Oops, electron. Yeah, right today. Fix that. Okay. Whose de Broglie wavelength is 0.2 nanometers. So I just usually call de Broglie wavelength like that, and it's 0.2 nanometers. I don't like nanometers, so the first thing I'm going to do is make that meters, like that, because nano means 10 to the minus 9. Okay, so de Broglie wavelength, if I go back and I look it up, the de Broglie wavelength of something is just h divided by momentum, which is m times v. Okay, they want me to find the speed, so I want to find v. So v is equal to h over m lambda, where lambda is the de Broglie wavelength. Well, I pretty well know all that, don't I? I know what h is. Again, this is Planck's constant. This is the mass of the electron. That's why they told me it was an electron. I can look that up in the book, or it's given in the front cover or something like that. And they told me what the de Broglie wavelength was. So I pretty well know everything I need here. So let me move that down where I can actually write something. So V is equal to H is 6.63, times 10 to the negative 34 joule seconds, divided by the mass of the electron is 9.11 times 10 to the negative 31 kilograms. You couldn't find a different time to get a drink of water? Okay. And then I've got my wavelength right here, which is 0.2 times 10 to the negative 9 meters. I'm sorry, my dog is so loud getting a drink of water. Apparently she's very thirsty. All right, so I'm going to multiply all that out, and that's going to give me the speed. All right. And then it says in the next part, what is the speed of a proton with this de Broglie wavelength? Well, now we've got a proton. So the equation is going to look exactly the same. Okay. Oops. That should be lambda. We're going to use exactly the same equation, except now the mass is going to be different. Now it's the mass of the proton. And the mass of a proton is 1.67 times 10 to the negative 27 kilograms. And if you don't know what that is, you look it up in your front cover of your book. Okay. So the setup is exactly the same. It's just instead of having an electron, now we have a proton. Okay. All right. So it's the same process as part A. So again, math is not super hard here. You've just got to know what the vocabulary is so you can put things in the right place. Okay. All right. Okay, so let's see. What else I had marked here? Okay, I'm going to skip over. Oh no, I want to do one more out of this thing. I want to do an uncertainty principle one. So we're going to do 53. All right, let's says the speed of an electron is known to be between 3.0 times 10 to the 6th meters per second and 3.2 times 10 to the meters per second. So delta speed is going to be 3.0 times 10. Whoops, I don't want to write it that way. It's between 3.2 and 3. So I'm going to take 3.2 times 10 to the 6th meters per second. And I'm going to subtract 3 times 10 to the 6th meters per second, because that's the range of my speed. That's my delta V. They told me it was between those two values. Okay, so that's pretty easy to figure out. That's 0.2 times 10 to the 6th. All right, it says, estimate the smallest possible uncertainty in its position. So this is the Heisenberg's uncertainty principle. And the Heisenberg's uncertainty principle says that the uncertainty in X times the uncertainty in a momentum is greater than or equal to H over 4 pi. Okay, well, where the uncertainty in speed shows up is the uncertainty in momentum is going to be equal to the mass of whatever it is times the uncertainty in V. And we know it's an electron again. So I want to find the uncertainty in the position. So the smallest possible uncertainty in the position is when this equation is equal. So for the smallest, well, if I could write today, uncertainty. Okay, let's try that again. Okay, smallest uncertainty is when the error or the variation in X over the variation in momentum is equal to H over 4 pi. Because if you'll notice this equation, it says greater than or equal to. Okay, so it's when that's equal is when we have the smallest uncertainty. So the uncertainty in X is going to be equal to H over 4 pi divided by delta P, which we really know is delta M times delta V. All righty, I think we know all that. So we know H is Planck's constant, so it's 6.63 times 10 to the negative 34 joule seconds over 4 pi times the mass of the electron is 9.11 times 10 to the negative 31 kilograms. And delta V, we figured out back up here, is 0.2 times 10 to the 6th. All right. And if you remember, what hides inside a joule is a Newton meter. And then what's a Newton? It's a kilogram meter per second squared. Your units will all work out and you'll end up with the error in X, or the uncertainty in X, by multiplying all that out. But when it says the smallest uncertainty, it's when you let that equation be equal. Okay, so this means smallest uncertainty right here, when you let that equation be equal instead of greater than or equal to, okay? All right. So it tells you the uncertainty by knowing when it told you that the speed was known to be between those two values, or it might say the position is known to be between those two values. And you take the difference between those to find the uncertainty. Okay? All right. Again, math is not hard. It's the terminology. You got to make sure you understand the vocabulary. All right. So now we're going to move over into chapter 29 a little bit and look at some problems there. Now, if you've had chemistry, this chapter may have seemed somewhat familiar, okay, because some of this stuff you have seen before, because chemistry and atomic physics are pretty much the same thing. All right. So we're going to look at number 6 to start with. It says how many electrons, how many protons, and how many neutrons are in the following thing. And the first thing they give you is lithium-6. All right. So the way you figure this out is you look up the atomic number for the atom, which in this case is 3. But the atomic number tells you the number of protons. So in this case, the atomic number is 3 Atomic number is represented by the letter Z. In this case, Z is equal to 3. So there's 3 protons. You look that up on the periodic table, you find that element. Okay. Up here, there's no plus or minus, so we assume it's a neutral atom. So there's no plus or minus, so we assume it's neutral. It'll have to tell you if it's a plus ion or a minus ion. So if it's a neutral atom, neutral atoms have the same numbers of electrons as protons. Okay, so if there's 3 protons, there's 3 electrons. Okay, all right, 3 electrons. Okay, then the last thing is this number right here. That's A, that's the atomic mass number. A is the number of protons plus the number of neutrons. Okay, so if that's 6, and I know I've got 3 protons already, that means I must have 3 neutrons to get that to add up to 6. Okay. All right. So let's do one more of these and then I'll leave the last one for you. The next one is carbon 13 with a plus. Okay, so I'm going to look up the atomic number of carbon, and I believe it's 6. Okay, so that means that there's 6 protons. Okay, now I've got a +1 or a 1 plus. So that means I've got 1 more proton than electrons. So if I've got 6 protons, I must have 5 electrons to make a +1 atom or +1 ion. Okay, then A is equal to 13. But that's the number of protons plus the number of neutrons. So if there's 6 protons, I've got to have 7 neutrons to add up to 13. So that's not too hard, right? All right. So again, not super hard if you know the vocabulary. And then I'm going to leave the last one for you. It's oxygen 18 double plus. So I'm going to leave that one to you to do yourself. Okay, so atomic notation, very useful. All right, sometimes this number here is called the isotope number, and we'll see that more in the next unit, but it's the atomic mass number or the isotope number. Okay, all right, let's do another one. So again, if you've had chemistry, this probably looks pretty familiar to you. Okay, let's look at let's look at 27. All right, 27 says when all quantum states or quantum numbers are configured or considered, how many different quantum states are there for a hydrogen atom in n equals 1 or n equals 2 or n equals 3? Okay, so we want to find the quantum number states combinations for n equals 1. All right, so n equals 1. So we have to remember the rules for the quantum numbers. So L is 0 up to whatever n minus 1 happens to be. Well, in this case, n minus 1 is 0. So the only possibility for L is 0. That's it. Okay. So n equals 1, L equals 0. Then M sub L ranges in value from minus whatever L is through 0 to plus whatever L is. So if L is 0, the only combination for M sub L, or the only possible value for M sub L, is also 0. Then M sub S doesn't depend on anything else. It's just chosen to be plus or minus 1/2. So in this ground state of hydrogen, there's 2 possible substates or subshells. There's 1, 0, 0 plus 1/2, and 1, 0, 0 minus 1/2. So there's 2 slots or 2 states for an electron to be in. So that's why when you talk about electron configuration, it's 1s2 is the most you can have, because this determines that it's an S state. So I could write this as electron configuration of 1s2. So this is determined by N, this is determined by L, and then this number is a combination of M sub L and M sub S. Okay. All right. Let's do the next state up, which is n equals 2, to practice one more time. Okay, so L goes from 0 to n minus 1. So my possible combinations here for L are 0 and 1. Okay. So if L is equal to 0, the only thing I can have for M sub L, again, is 0. And I have an M sub S of plus or minus 1/2. So that's going to be like what I had before. But if L is 1, or excuse me, L is 1, okay, because L can be up to n minus 1. So n was 2, so L can be 1. So then M sub L could be minus 1, 0, or plus 1. Okay. So I've already got that state there. Okay. So, and then M sub S can be plus or minus 1/2 for these guys. So my possible quantum number combinations are 2, 0, 0, plus 1/2. I keep writing that down. Plus 1/2. 2, 0, 0, minus 1/2. So that would be my 2s2 state. So this is my N, this is my L, and this is my combination of M sub L and M sub S. Or I can have 2, 1, minus 1, plus 1/2, plus 1/2. I could have 2, 1, minus 1, minus 1/2. I can have 2, 0, 0, plus 1/2. I could have 2, 0, 0, minus 1/2. Or no, excuse me, I'm writing that down wrong. This should still be 1. Because my M sub L, my L, it could have the minus 1, 0, 1. I'm sorry, I got that wrong. So, or I could have 2, 1, 1, plus 1/2. Well, I keep trying to write that together. And 2, 1, 1, minus 1/2. So I take this row and write down all the combinations. So this row right here is these 2. And then this row right here are these 6. So that's why I can also have 2p6, because this is N. When L is equal to 1, that's the p state. And I have 6 possible combinations of M sub L and M sub S in that p state. Okay. All right. So the S state is when L is equal, the P equal to 0. The P state is when L is equal to 1. D is when L is equal to 2, and so on. So you write down all the possible combinations. So you keep this is in, this column is your L. And then you change all the different possible values of M sub L and M sub S you have to count up how many possible states you could have. Okay, so that's why P6, 6 is the most you can have in a P state because there's 6 combinations of the quantum numbers. Okay, all right. All right, and then n equals 3. I'm going to let you guys do that one on your own, but you do it the same way. I'll get you set up for it real quick. So if n is equal to 3, then L can be 0, 1, or 2. Okay, so for L equals 0, M sub L is still equal to 0, and M sub S is still equal to plus or minus 1/2. For L equals 1, M sub L can be -1, 0, or +1, with an M sub S for each one of plus or minus 1/2. So it's just like what I just did. But then if L equals 2, M sub L can be -2, -1, 0, 1, or 2. So you'll have another set of numbers that has a column that looks like this, except it'll be 3. It looks like this one up here, except it'll be 3, 1, -1, and so on. So you're going to have 10 there, 10 different combinations. So you'll write down a column just like I did here up at the top, like I did here, except I'll have these will be for your 3, and then this will be 2, and then you'll start with -2, plus or minus 1/2, -1, plus or minus 1/2, 0, plus or minus 1/2, 1, plus or minus 1/2, and 2. So you're going to have 10 terms there instead of 6. Okay? All right. So I'll let y'all count those up on your own. You can do that. All right. Okay, I want to look at another one here. I want to look at 34. 34 says to identify, for each element, identify the element for each of these electron configurations. Determine whether this state is the ground state or an excited state. All right, so 34, I've got 1s2, 2s2, 2p5. Okay, so for the S state, these are full. Okay, this one could have room for one more, so it's not full yet, and I don't have any more states, so this is in the ground state. That means the electrons are in their lowest energy state, okay, because I haven't jumped up and started putting electrons in a higher shell without filling everything below. So that means it's ground state. To figure out what element it is, I take 2 plus 2 plus 5, and I get 9. And then I go look at my periodic table and see what element number 9 is. Okay. And I don't remember what element number 9 is. It's probably like fluorine, not fluorine. Is it sodium? I don't remember. I know all the upper elements. I don't know the lower ones. Number 9 is, yeah, fluorine. So it's number 9, so it's fluorine. Okay. All right. Part B gives me this one. 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p. Okay. So I've got to figure out what is the order of filling here. Now remember, there are rules about the order that these things fill, okay? And they start to cross over, and that's when we get into those transition elements, okay? So what happens is I have to go back and look, and a good picture to look at is figure 2922 in your book. And it shows the order of filling, okay? So if I look at this, the order of filling is like this, all right? It goes 1s, the 1s state, then the 2s state, then the 2p state, then 3s, 3p, 4s has to fill before 3d and 4p. Okay, so 4s has to fill first, so really it goes here in terms of the ordering. Okay, then 3d fills, and then 4p is after 3d. Okay, and that's because the amounts of energy they have, those elements, those start to overlap. So this is figure 2922 in your book if you want to look at the order. Okay, so this is full. The S states need 2, so those are full. P's are 6, so that's full. That's full. P's full. 4s is full. Then I need to look at 3d, and 3d, how many electrons can it have? Well, if I count, it can have 10, so that's full. And then the last thing I'm left with is 4p, and there's only 1 in there, but it's filled all the layers below that. So this is another ground state. Okay, this is another ground state because I'm filling the shells in the order of their energy, so that's okay. So I need to know what element this is. So I've got 2 plus 2 plus 6 plus 2 plus 6 plus 10 plus 2 plus 1. Because I've got 1 electron in that last state. So that's 10, 12, 18, 28, 30, 31. So this is 31. So I'm going to go back and look in my periodic table, which I should have marked. The dogs are being wild today. 31. And 31 is gallium. 31 is gallium. So you just count up all the electrons, okay? If I added that up right, y'all can check my math, but you can look it up and see. Okay, so that's a good kind of overview of the types of problems that you're going to see in this unit. It gives you some examples to look at. So you can go back and kind of go over these a little bit. Again, the math here is not hard. It's just, you know, you've got to know the terminology to make sure you put things in the right place. Okay. All right. So that's all the problems we're going to do for today. I will get this posted on Zoom as soon as I can. And I will either see you guys as you're doing your presentations, or I will see you for our next problem session, which will be our last problem session. So I will see you then. Goodbye, everybody.